Hello, friends, and welcome back to The Snoozy Scientist, where we gently explore the mysteries of our world, one sleepy yawn at a time. I'm so glad you've chosen to spend a little piece of your evening, your morning, or perhaps somewhere peacefully in between, winding down with me. Tonight, we are drifting back in time to an age that seems to have slipped through Earth's own memory. Imagine opening the diary of our planet only to find that an entire billion-year chapter has been torn away. A stretch of time longer than the distance from the first animals to us vanished, as though it never happened. From 1.8 to zero point 0.8 billion years ago, Earth seemed to fall into an uncanny stillness. No great extinctions, no sudden ice ages, no booming forests or stampeding dinosaurs, just stillness for a billion years. Scientists call it the boring billion, a name that suggests nothing of note happened, and yet the truth is far stranger, because beneath that quiet, hidden revolutions were stirring. Mother Nature was conducting experiments that would one day rewrite the rules of evolution forever. This was Earth's long meditation, the calm before the storm, the slow breathing of a planet preparing for an explosion of life that would burst forth in dazzling complexity. Without this quiet chapter, the Earth we know, filled with plants, animals, and even humans, might never have come to be. But how can an entire billion years of life's story simply disappear? What was it that Mother Nature was secretly cooking? What was Earth really preparing for? Tonight, we'll step softly into this lost world to uncover how the stillness of this age may have been the very reason life like ours was ever possible. But before we begin, if you find comfort in these quiet journeys through science stories, it would mean the world to me if you gave this video a gentle like and maybe tapped subscribe. It helps more curious minds like you discover this peaceful little corner of the internet and tells the algorithm that sleep and science belong together. And if you'd like to share, let me know in the comments, where are you listening from tonight and what time is it there? I love seeing how far across the world these soft explorations travel. Now take a deep breath, let your shoulders soften, and together let's step softly into Earth's lost billion years. When geologists look back into the deep past, they do so by reading the layers of stone beneath our feet. Each layer is like a page in Earth's diary, pressed down over time by rivers, oceans, winds, and ancient environments long gone. Normally, these pages follow one after another in an orderly stack, telling us of shifting seas, volcanic eruptions, and the rise and fall of climates. Yet when scientists began studying some of Earth's most famous landscapes, they discovered that enormous sections of the book were gone. Not just a few pages, but entire chapters ripped away. Perhaps the most famous example lies in the cliffs of the Grand Canyon. There, layers of rock dating back nearly 2 billion years sit directly beneath rocks that are only about 500 million years old. In between those two, a gap of more than a billion years is missing. Geologists call this strange absence the Great Unconformity. The layers we would expect to see from that long period of time simply are not there. They were either eroded away, never deposited, or recycled back into the Earth's restless crust. To stand before those towering canyon walls is to look directly at the mystery. You can place your hand on ancient Vishnu schist, formed nearly 2 billion years ago, and then raise it to touch Cambrian sandstone, laid down when strange soft-bodied creatures crept across the seafloor about 500 million years ago. Between those two, an unimaginable span of time vanishes into silence. The world had changed in profound ways during that gap, yet the record is gone, as if the planet itself had deliberately erased its own memory. What makes this absence so baffling is how widespread it is. The Great Unconformity is not confined to the Grand Canyon alone. Rock records from every continent show similar gaps. Mountains, valleys, and coastal cliffs across the world reveal the same disappearance. A billion years, sometimes more, stripped out of history. This is not a local oddity, but a global silence, a missing chapter written into the very bones of the planet. Scientists have proposed many explanations for this mystery. One possibility is erosion on a scale so vast it is difficult to imagine. Over countless ages, entire mountain ranges may have been worn down to nothing, their sediments swept into oceans and scattered across the seafloor, leaving behind no trace of the original formations. Another possibility lies deeper still within the planet's shifting crust. Through the long cycles of plate tectonics, whole regions of rock could have been dragged down into the mantle and recycled, their stories melted away in the slow churn of Earth's interior. What complicates the mystery is that this missing record coincides with some of the most critical transitions in Earth's history. During this gap, life was quietly reshaping itself. Continents were gathering and breaking apart. Oxygen levels in the air were balancing in delicate ways. Yet the physical evidence of these transformations is patchy at best. We know the events must have happened because their consequences are visible in later rocks and in the DNA of the living world. But the record itself is faint, like an echo heard through thick walls. To peer into the great unconformity is to peer into absence. It is a silence that has both frustrated and fascinated generations of scientists. Each missing layer hints at lost worlds, vanished rivers, erased coastlines, and ecosystems we will never fully see. In this gap may have been entire landscapes where microbial mats spread across shallow seas, or volcanic plains that stretch toward hazy skies, all of it swept away, leaving only a haunting space between what came before and what followed after. The strangeness of this absence does not weaken our understanding, it deepens it, for it reminds us that Earth is not a passive recorder of history. It is an active and restless planet, forever writing and rewriting its own story. Where we expect continuity, we often find disruption. Where we expect answers, we sometimes find silence, and in that silence, our curiosity grows sharper. From the stillness of missing rocks, we turn now to the name scientists gave to this long forgotten age, a name that hides the true depth of its secrets. They called it the boring billion. When geologists first began to piece together the vastness of Earth's history, they noticed something peculiar. In earlier eras, the rocks told vivid stories of upheaval and catastrophe. There were signs of global ice ages, sudden bursts of volcanic fury, and dramatic shifts in the chemistry of the oceans. Later eras gave us the rise of animals, forests, and life in bewildering abundance. But the stretch of time between 1.8 and 800 million years ago seemed strangely subdued. The rocks preserved from this age spoke of stability, of landscapes that lingered without great drama, of seas that remained much the same for unimaginable spans of time. To capture this quiet in a single phrase, scientists began calling it the boring billion. The term carried a note of frustration as well as description. To those trying to piece together the story of life, it seemed as if the planet had slipped into a kind of slumber. Fossils from this billion-year window revealed little more than microbial mats and simple stromatolites. Chemical records suggested that oxygen in the atmosphere held steady, neither dropping to suffocate life nor rising high enough to spark an explosion of diversity. For the geologists searching for clues of rapid change, this period appeared uneventful, a long plateau of monotony that stretched on and on. Yet with every passing decade, research has shown that the phrase boring billion is more of a misdirection than a reality. While Earth's surface may have appeared calm, deep within its oceans and within the very cells of its inhabitants, revolutions were quietly unfolding. These were not the kinds of revolutions that leave dramatic scars on the landscape. They were subtle, slow, and easily overlooked, but they shaped the very foundations of the world to come. Consider what it meant for oxygen to hold steady. After the Great Oxidation Event, when oxygen first began to build in the atmosphere, the planet could easily have tipped back into an anoxic state. Instead, during the boring billion, Earth found a delicate balance. Though the air was far from what we breathe today, it was enough to allow early eukaryotic cells to take root and begin their long silent work. This balance gave life the breathing space to prepare for future leaps. The same is true of the continents. During this period, vast land masses assembled into supercontinents that drifted across the globe. Though they moved slowly, their presence altered the cycles of nutrients flowing into the seas. Rivers carried phosphorus and other vital elements into shallow waters, where microbial life grew in carpets. These mats of life did not look impressive from afar, yet they were laying the groundwork for more complex ecosystems. Even within the smallest of cells, experiments were underway that would change evolution forever. It was during this billion-year span that sexual reproduction appeared, quietly rewriting the possibilities for how organisms could share and shuffle their genetic codes. With sex came the promise of faster adaptation, the hidden key that would one day unlock the Cambrian explosion. From the outside, nothing seemed to move, but within the microscopic realm, the rules of life were being rewritten in silence. The irony of the boring billion lies in this very paradox. On the surface, the Earth seemed to rest. There were no world-shattering extinctions, no great bursts of animal diversity, no dramatic swings of climate like the snowball ages to come. To a casual glance, it was a static age, but when viewed through the slow patience of geology and biology, it was anything but boring. It was a long preparation, a planetary breath, a quiet rehearsal before the curtain would rise on a far more spectacular show. This is why many scientists now view the label with suspicion. What was once thought to be a dull interlude is increasingly recognized as one of the most important intervals in Earth's history. Without its quiet stability, there may never have been a chance for complexity to emerge at all. The stillness was not absence, it was opportunity. The calm surface was deceptive, for underneath, the engines of life and planet were working tirelessly. From this paradox of silence and revolution, the story now moves deeper into the heart of what was happening in those hidden places. For within this so-called boring age, the first truly complex cells were rising, carrying within them the potential for every form of life we know today. In the quiet stillness of the boring billion, a silent revolution was taking place. For hundreds of millions of years, life on Earth had been simple, made up of prokaryotic cells that carried no nucleus and little internal structure. These organisms, bacteria and archaea, had already transformed the planet, once by releasing oxygen and shaping the chemistry of the seas. But as remarkable as they had limits. Their small size, their simple architecture, and their reliance on single strands of genetic material held them to a world of microscopic possibilities. Then, somewhere within this long era of apparent calm, something extraordinary occurred. A new kind of cell emerged, more intricate, more flexible, and far more capable of innovation. These were the first eukaryotes, cells with a true nucleus that sheltered their DNA, and with compartments that divided up the work of life. Unlike their simpler cousins, eukaryotic cells could grow larger, process energy more efficiently, and support a complexity that prokaryotes never could. This leap is considered one of the most important in the history of evolution. It was not dramatic on the surface. The oceans did not suddenly bloom with plants and animals, and the continents did not suddenly shake with movement. Yet hidden in this cellular architecture was the potential for everything that would follow. Without eukaryotes, there could be no multicellular organisms, no nervous systems, no forests or coral reefs, and certainly no humans. In a sense, the emergence of the eukaryotic cell was as momentous as the origin of life itself. How it happened is still a matter of investigation, and the story reads almost like a tale of cooperation born from necessity. Many scientists believe that eukaryotes arose through a process called endosymbiosis. In this scenario, one simple cell engulfed another, but instead of digesting it, the two formed a lasting partnership. The engulfed cell eventually became the mitochondrion, a tiny powerhouse that generated energy with remarkable efficiency. This event may have taken place more than once, giving rise to variations of eukaryotes, but the results were the same. With mitochondria working within them, these new cells gained the energy surplus to grow larger and more elaborate. Fossil evidence offers faint but intriguing glimpses of this transformation. Around 1 billion years ago, in what is now northern Canada, rocks preserved the remains of Bangiomorpha, a form of red algae. These microscopic fossils are among the earliest direct evidence of complex multicellular eukaryotes. They show filaments and branching structures that hint at coordinated growth, a sign that individual cells were working together as part of a larger whole. Though humble by modern standards, these algae marked the beginning of a path that would lead, hundreds of millions of years later, to forests, flowers, and entire ecosystems built of cooperating cells. The power of the eukaryotic design lies in its flexibility. By housing DNA within a nucleus, genetic material was better protected and better organized. This allowed for larger genomes and more intricate instructions for building proteins, which in turn opened the door to greater diversity. Internal compartments, called organelles, divided up the labor, so some parts of the cell specialized in energy, others in protein building, others in packaging and transport. This division of labor mirrored what would later occur in whole multicellular organisms, where tissues and organs took on specific roles. In many ways, the eukaryotic cell was a miniature rehearsal for the complexity of animals and plants. Even though these cells were tiny, their significance cannot be overstated. For nearly 1 billion years, they laid the groundwork in silence. They spread across oceans, sometimes clustering in colonies, sometimes living solitary lives. They were still invisible to the naked eye, yet they carried within them the blueprint for eyes, limbs, wings, and brains that had not yet come into being. This hidden transformation explains why scientists no longer view the boring billion as truly boring. On the surface, the world may have seemed stagnant, but inside the cellular realm, evolution had taken a daring leap. The shift from prokaryotes to eukaryotes gave life a new canvas, one vast enough to support all the future complexity of the biosphere. As the eukaryotes continued to refine their inner workings, another quiet innovation was beginning to emerge, one that would make evolution even more dynamic. In this same age of stillness, life discovered the exchange of genes through sexual reproduction, a process that would forever alter the rhythm of survival and change. In the deep stillness of Earth's long billion-year meditation, life was making quiet but daring experiments. Among the tiny eukaryotic cells that had begun to populate the oceans, something remarkable was unfolding. It was not visible to the naked eye, nor did it leave behind towering fossils that would catch a geologist's attention. Instead, it was hidden within the invisible exchanges of genetic material, a subtle new rhythm in the story of survival. For billions of years before this, life had relied only on the simplest of strategies to continue. Cells divided, one becoming two, then two becoming four. Each offspring was nearly identical to its parent, a perfect copy carrying the same genes, the same instructions, and the same vulnerabilities. This kind of replication was efficient, and it kept life going through unthinkable stretches of time. But there was a cost. Without change, life had little room to adapt. Each lineage was like a long, unbroken mirror, endlessly reflecting itself into the future, but always with the same cracks. Somewhere within the boring billion, that mirror began to fracture in a new and creative way. Eukaryotic cells discovered the act of recombination. Instead of endlessly copying themselves, some cells began to share. Two individuals would come together, their genetic material intertwining, mixing and producing offspring that were not simple replicas, but unique blends of both. This was the dawn of sexual reproduction. It is hard to imagine how quiet and unassuming this shift must have looked. To the oceans above, nothing seemed different. Microbial mats still coated the shallow seafloors, stromatolites still rose in their patient domes, and the waters remained filled with life, too small to see. But at the microscopic level, something profound had changed. Life was now testing variety, reshuffling its genetic cards with each generation. The advantages of this new system were immense. With each act of recombination, new combinations of traits appeared. Some offspring were weaker, some no different at all, but others carried subtle changes that gave them an edge. Perhaps a slightly more efficient way of using nutrients, or a better tolerance for the low levels of oxygen in the seas, or resilience to toxins drifting through the water. Whatever the advantage, these offspring had a better chance of survival, and in time, they passed their successful traits onward. Sexual reproduction introduced a kind of creativity into the process of evolution. Instead of waiting for rare mutations to bring novelty, life could now generate diversity in every generation. With diversity came resilience. Populations could adapt more quickly to shifting conditions, even if those shifts were slow and subtle. This flexibility would become the foundation for the explosive variety of forms that appeared later in Earth's history. Fossil evidence of this quiet revolution comes to us in fragments, in ancient rocks over 1 billion years old. Paleobiologists have found signs of multicellular algae that appear to have reproduced sexually. These fossils are small, little more than filaments of cells branching into delicate patterns, but they carry hints of alternation between sexual and asexual stages of life. It is in these microscopic traces that we glimpse the earliest experiments in genetic sharing, the first known evidence of sex between single-celled organisms. What is striking about this moment is not just its practicality, but its poetry. In a world where life had survived by copying itself endlessly, two cells discovered that by coming together, they could create something new, something that neither could produce alone. It was as if life itself had begun to whisper the idea of partnership, testing the notion that strength could be found in union, not just repetition. Though it would take hundreds of millions of years for sexual reproduction to become widespread and to shape the diversity of multicellular organisms, its origins in the boring billion show how even in times of apparent stillness, life was quietly rewriting its own rules. These small, unseen unions gave rise to the endless variety that would one day cover the earth with forests, reefs, and creatures of every shape and size. From the hidden intimacy of single cells exchanging their secrets, the story of life continued, always building on quiet foundations. And as these cells experimented with new ways to endure and adapt, the larger world around them remained subdued, holding life in a long pause that seemed to stretch forever. Yet even in this pause, the oceans were alive with subtle struggles. Conditions of scarcity and chemical imbalance still shaped the possibilities of what life could achieve. It was within this context that life's long stagnation unfolded, a period where the promise of complexity remained contained, waiting for its moment to bloom. Even with the arrival of eukaryotic cells and the quiet beginnings of sexual reproduction, the world above the waves appeared largely unchanged. For hundreds of millions of years, the seas remained a microbial world. There were no forests to soften the coasts, no creatures crawling along the land, no swarms of animals filling the oceans. Instead, the planet was still ruled by organisms far too small to see without a microscope. The fossil record of this time shows us the same patient builders that had been present for ages before. Stromatolites continued to thrive in shallow seas, their domed layers formed by the steady activity of microbial mats. These structures rose slowly, millimeter by millimeter, as mats of cyanobacteria trapped sediments and built stony reefs that could last for thousands of years. Some of these stromatolites grew large enough to shape entire coastlines, standing as the quiet monuments of a world still in waiting. Microbial mats covered tidal flats and shallow lagoons, forming living carpets that spread like vast biological blankets. They had no flowers, no branches, no movement, yet they were communities in their own right, filled with countless microscopic inhabitants bound together in thin layers. Within those mats, different microbes played different roles, some producing oxygen, others breaking down waste, all coexisting in a balance that had endured for eons. But despite this persistence, life did not make the leap to greater complexity. Eukaryotic cells existed, and the spark of genetic recombination had been lit, but evolution seemed to move at a glacial pace. The oceans of the boring billion held a promise that never quite blossomed. Scientists believe that part of the reason for this stagnation was the lack of available nutrients. For complex organisms to flourish, elements like phosphorus are essential, fueling energy and growth. During this long period, those nutrients were in short supply. Rivers carried less phosphorus into the seas, and much of what was available sank to the seafloor, locked away from the reach of surface life. Oxygen, too, played its part in holding back evolution. The air contained some oxygen, more than in the earliest days, but far less than today. The oceans themselves remained stratified, with shallow waters carrying limited oxygen, while the depths stayed suffocating and hostile. In many places, mid-level waters were rich not in oxygen, but in hydrogen sulfide, a gas deadly to most modern organisms. For life in these conditions, survival meant staying small and simple. Larger, more energy-hungry creatures could not thrive in such an environment. The result was a world that looked static from afar, even as tiny changes were unfolding invisibly. Vast stretches of shallow seas shimmered under ancient sunlights, their floors coated with microbial mats that rose and fell with the tides. Occasionally, colonies of early eukaryotes may have clustered, branching into fragile filaments like those seen in ancient fossils of red algae. Yet these small experiments remained rare, flickers of complexity that never expanded far. For most of this billion-year chapter, Earth's biosphere remained caught in a holding pattern, waiting for something more. It is tempting to imagine this age as empty or uneventful, but the truth is more nuanced. The patience of microbial life was not a weakness, but a kind of endurance. In the face of limited oxygen and scarce nutrients, these simple organisms persisted. They cycled elements through the seas, maintained fragile balances, and slowly altered the chemistry of the planet. Each stromatolite dome and each mat of cyanobacteria was part of a vast, hidden machinery keeping Earth alive. The calmness of this world is part of what makes the boring billion so paradoxical. Evolution had already achieved the leap to complex cells, yet the stage for multicellular life was not ready. It was as if the planet itself was holding its breath, suspended between potential and possibility. While life endured in this subdued state, the oceans themselves held secrets far more hostile. Beneath the shallow, oxygen-poor surface waters, deeper realms carried toxins that shaped what was possible for early organisms. To step further into this world is to enter seas that were not only stagnant but poisonous, places where the chemistry of the water itself limited the horizons of life. Beneath the still waters of the Proterozoic seas, where eukaryotic cells drifted quietly and microbial mats carpeted the shallows, there existed another world, darker and far more dangerous. The upper layers of the ocean held only limited amounts of oxygen, just enough to support small colonies of microbes. But once you sank deeper, beyond the reach of sunlight and surface mixing, the chemistry of the water changed. Instead of oxygen, the deep seas were saturated with hydrogen sulfide, a gas deadly to most modern organisms. This kind of ocean is described as euxenic, a place where oxygen is absent and sulfur-loving bacteria thrive. For us, hydrogen sulfide is a poison capable of suffocating cells and disrupting the delicate machinery of life. Yet for the microbes of that time, it was both a danger and an opportunity. Some organisms adapted to live in these hostile depths, harnessing chemical reactions involving sulfur for energy. But for most forms of life, these seas were inhospitable, forbidding the spread of larger and more complex creatures. The persistence of anoxic and exinic conditions for hundreds of millions of years raises deep questions. Why did the oceans remain so suffocatingly stable for so long? Part of the answer lies in the balance of Earth's early atmosphere. While oxygen had risen after the Great Oxidation event, it never reached modern levels during the Boring Billion. The small amounts that did exist were largely confined to the shallowest layers of the seas, where photosynthetic microbes released it into the water. Strong stratification kept that oxygen from mixing downward into the deeper waters. Instead, the depths remained cut off, a stagnant reservoir where sulfate-reducing bacteria flourished, producing more hydrogen sulfide and reinforcing the toxic environment. The configuration of continents may have also played a role. During this time, supercontinents such as Columbia and Rodinia were forming and drifting across the planet. Their massive size altered weathering patterns, nutrient delivery, and circulation in the seas. With limited nutrient input and stable climates, there were fewer disruptions to break the cycle of anoxia. Ocean currents remained sluggish, preventing the deep and surface waters from blending, and so the poison depths endured for ages beyond imagining. For life, the impact was profound. The shallow, oxygen-poor surface waters could support only a narrow range of organisms. The deep, euxenic layers created an invisible ceiling that life could not easily cross. Multicellular organisms, which would require abundant oxygen, could not spread in such a world. Complex animals were impossible, while much of the ocean remained locked in this hostile state. Evolution was not halted, but it was slowed, confined to niches where oxygen was present in small amounts and where microbes had carved out stable roles. The fossil record reflects this strange stability. Stromatolites and microbial mats remained dominant, their domes and carpets persisting across shallow seas. The tiny red algae discovered in billion-year-old rocks were exceptions, fragile outposts of complexity that managed to survive in scattered pockets. For the most part, however, the oceans were a layered prison, with life confined to the margins. It is a sobering thought that for nearly 1 billion years, most of Earth's seas were unfit for anything resembling modern marine life. Imagine vast stretches of ocean stretching from horizon to horizon, their surfaces calm under ancient skies, Yet beneath that stillness, the waters turned toxic. The deep blackness carried not the oxygen of our familiar oceans, but suffocating sulfur, invisible and lethal. This hidden poison shaped what life could become and set strict boundaries on what was possible. Yet within this limitation, evolution still found ways forward. Microbes adapted to the chemical extremes, finding niches in the balance of oxygen and sulfur. These quiet survivors kept the cycle of life turning, maintaining a fragile foothold in a world that seemed unwilling to change. As the oceans remained stratified and suffused with hydrogen sulfide, evolution bided its time. Only when conditions shifted would the full potential of eukaryotes and sexual reproduction be realized. For now, life persisted in shallow refuges, waiting for oxygen to one day rise higher and for the poisoned seas to finally relent. The story of these toxic waters leads directly into the puzzle of oxygen itself and why it lingered at such low levels for so long. Understanding that plateau is key to knowing why Earth seemed to hold its breath during the boring billion. Long before the quiet billion years began, Earth had already undergone one of its greatest revolutions. Around 2.5 billion years ago, tiny photosynthetic microbes released oxygen into the atmosphere for the first time in significant amounts. This event, known as the Great Oxidation, transformed the chemistry of the planet. For the first time, free oxygen existed in the air and in shallow waters, reshaping climates, altering rocks, and forcing many early organisms that thrived without oxygen into decline. It was as if the planet had suddenly shifted gears, opening a new chapter in the history of life. In the aftermath of this upheaval, oxygen levels rose sharply, reaching what scientists sometimes describe as an overshoot. For a time, there may have been more oxygen than could be sustained by the slow balance of production and consumption, but this spike did not last. Instead of continuing to climb toward modern levels, oxygen stabilized at relatively low concentrations. For nearly 1 billion years, throughout the boring billion, the planet seemed to settle into a long plateau. The air contained more oxygen than in the earliest days, but far less than what animals would later require. Why oxygen paused here, balanced between scarcity and abundance, remains one of the great puzzles of Earth's history. Part of the answer lies in the cycle of nutrients. For oxygen to accumulate in the air, photosynthetic organisms must produce it in large amounts and store the carbon that fuels it. But nutrients like phosphorus, essential for photosynthesis, were in short supply during much of this time. Rivers delivered only small amounts to the oceans, and much of it sank into sediments, where it became locked away. With nutrients limited, oxygen production could not surge. Another factor was the chemistry of the oceans themselves. Deep waters remained anoxic, filled with sulfides and iron that readily consumed any oxygen drifting downward. This created a chemical sink that kept oxygen levels from rising higher. Whenever oxygen tried to expand its reach, the oceans absorbed it, binding it into minerals or fueling bacteria that thrived on the balance between oxygen above and poison below. The planet was maintaining a delicate equilibrium, one that held steady for ages. For life, this plateau created strict boundaries. Eukaryotic cells existed, and the beginnings of sexual reproduction had appeared, but without more oxygen, the energy needed to support larger bodies and more active metabolisms was unavailable. Complex animals, with their demand for constant oxygen flow, could not yet evolve. The world remained microbial, its diversity rich in the small and unseen, but unable to leap into visible abundance. It is striking to think that for nearly 1 billion years, oxygen levels lingered in this middle ground. enough to sustain photosynthetic mats along coastlines, enough to allow early eukaryotes to drift and divide, but never enough to open the gates to true multicellularity. It was a planet holding its breath, balancing on the edge of greater possibilities, yet not tipping forward. Some scientists see this long plateau as essential. The stability may have given life the time it needed to refine its molecular machinery, to experiment quietly with complexity before oxygen finally rose again. The patience of the biosphere, set against the slow breathing of the planet, meant that when oxygen levels did climb higher at the end of the boring billion, life was ready to take advantage. Still, the paradox remains haunting. After the great oxidation, why did oxygen not simply continue its climb? Why did Earth spend so long in this middle state, where possibility seemed trapped behind a barrier that would not break? The answers lie not only in the atmosphere, but in the chemistry of oceans, the cycling of continents, and the unseen interactions of microbes that consumed as much oxygen as they created. This oxygen plateau shaped the destiny of life. It created a ceiling that held animals back, confined complexity to whispers, and prolonged a world of microbes for almost 1 billion years. Only when the balance shifted, when conditions changed enough to free oxygen from its chemical traps, would Earth step into a new phase of abundance. From the stillness of this long plateau, the story moves now to the faint traces of movement that began to appear in sediments. Even in a world of microbial mats and poisoned seas, life was beginning to stir in ways that hinted at the first shadows of animal behavior. For much of the boring billion, life existed in stillness. Microbes coated the seafloor in mats that barely shifted with time, and eukaryotic cells drifted gently through the water, carried by currents rather than by choice. It was a world of repetition, of quiet persistence, of forms that endured without reaching toward greater motion, but buried within this silence are faint signs that not everything was as motionless as it seemed. In rocks laid down during this long interval, scientists have discovered tiny markings etched into ancient sediments. They are not the fossilized remains of bodies, but the traces of activity, subtle signatures of organisms that once moved across or within the seafloor. These markings, known as trace fossils, hint at a kind of behavior beyond simple floating or passive growth. They suggest that some microbes, or perhaps early multicellular forms, were beginning to crawl or burrow, leaving behind patterns that still whisper across the ages. The idea is astonishing in its simplicity. Instead of being locked in place within microbial mats, some organisms seem to have gained the ability to push through sediment, to search for food, or to avoid unfavorable conditions. Even the smallest change in behavior would have been significant in a world otherwise ruled by stasis. These tiny shifts mark the difference between being at the mercy of the environment and beginning, however tentatively, to respond to it. The markings themselves are delicate, often no more than faint grooves or winding channels pressed into the rock. Some are short and shallow, like the imprint of a tiny body settling briefly before being covered by sand. Others form longer tracks that curve and twist, suggesting that the organism moved deliberately, however slowly, as it pressed forward in search of nutrients. To the trained eye of a paleobiologist, these subtle impressions are profound. They reveal not just the presence of life, but the first hints of action, of intention, of interaction with the environment in a way beyond simple existence. It is important to remember that these were not animals as we know them. There were no fins or legs, no shells or skeletons. These were likely colonies of microbes, or early multicellular bodies, so simple they would be invisible to us without a microscope. Yet even in their simplicity, their traces tell a story of change. Life was beginning to test new possibilities, experimenting with motion as a way to survive. The appearance of these trace fossils opens a window into the very beginnings of animal like behavior. Motion, even at the smallest scale, allowed organisms to explore, to find new pockets of nutrients, to escape zones where toxins collected, and to spread beyond the limits of static mats. Each track, each groove, is evidence of life pressing against the boundaries of stillness, searching for opportunity. What makes these early traces so compelling is their rarity. They are not abundant, scattered only in certain sediments, as if movement was still an experiment, fragile and uncertain. For long stretches of the boring billion, the oceans show no signs of such activity at all. Yet where they do appear, they signal the first stirrings of a capacity that would later define entire kingdoms of life. From these faint marks would one day emerge the wriggling of worms, the scuttling of trilobites, and the swimming of fish. It is almost poetic to imagine the first stirrings of motion on a planet still held in long equilibrium. For hundreds of millions of years, life had endured in patience, rooted to seafloors or drifting passively with currents. Then, quietly, some forms began to leave their marks, shallow lines in soft sediment, a record of their fleeting presence. They did not know it, but they were laying down the very first steps on a path that would eventually lead to the restless, ceaseless activity of the animal kingdom. These glimpses of movement are among the earliest signs that life was preparing for something more. They are whispers of future revolutions, subtle indications that behavior itself was becoming part of evolution's toolkit. And from these faint tracks in ancient stone, the story flows into the earliest experiments in multicellularity, where individual cells began to bind together and form bodies that were greater than the sum of their parts. For hundreds of millions of years, life's story was told in single cells. They grew, divided, and drifted through the oceans, content to exist as solitary units or in thin mats layered across the seafloor. Yet hidden within the stillness of the boring billion, there are faint but remarkable signs that life was beginning to experiment with something new. Instead of surviving as individuals, some cells began to join together, cooperating as parts of a greater whole. These were the first fragile steps toward multicellularity. The fossil record gives us delicate glimpses of this shift. In rocks more than 1 billion years old, paleontologists have found the remains of Bangiomorpha, an ancient red alga. Under a microscope, these fossils reveal filaments of cells arranged in branching patterns, suggesting growth that was coordinated rather than random. Unlike simple microbes that merely divided and drifted, these cells work together to build structures, each division leading not to separation, but to the expansion of a shared body. Bangiomorpha is often described as the earliest known example of a multicellular organism, and its presence in the rocks of northern Canada marks a quiet milestone in the history of life. There are also hints, though debated, that some of the earliest sponges may trace their origins to this time. Certain chemical markers preserved in ancient sediments resemble compounds produced by modern sponges, leading some scientists to wonder whether these simple animals had already begun to emerge. If true, it would mean that the ancestors of animals, however modest in form, were already present in the oceans long before their eventual flourishing. Yet these early experiments in complexity did not spread widely. The red algae remained rare, small, and limited to specific environments. If sponges existed at all, they were confined to narrow habitats, leaving only the faintest traces of their presence. Multicellularity had arrived, but it did not yet thrive. The reasons lie in the conditions of the time. The oceans still carried limited oxygen, often restricted to shallow waters near the coasts. The deep seas remained hostile, filled with hydrogen sulfide and devoid of oxygen, creating vast regions where larger organisms could not survive. Nutrients were also scarce, with phosphorus and other essentials delivered in small amounts that favored simple microbes rather than larger, energy-demanding bodies. In such a world, multicellular life faced heavy obstacles. Still, the attempt itself was extraordinary. Within those fragile filaments of algae and possible sponge-like creatures, life was testing cooperation. Multicellularity offered possibilities that single cells could never achieve. Groups of cells could divide labor, with some specializing in capturing energy, others in reproduction, and others in protection. They could grow larger, expanding into new shapes and structures that would one day become the foundation for plants, animals, and fungi. These first steps may have been tentative, but they carried within them the seeds of everything that would follow. It is humbling to imagine these early forms scattered in isolated patches across ancient seas. They were not the thriving forests or bustling coral reefs we know today, but faint glimmers of what could be. A filament of red algae swaying in shallow water, or a sponge-like form filtering nutrients along a sheltered coast, may have seemed unremarkable in its time, yet each represented a profound change in life's story. The quiet beginnings of multicellularity remind us that revolutions do not always arrive with sudden force. Sometimes they begin as whispers, with a few scattered organisms daring to try something new. Most of these experiments may have failed, leaving no record behind. But those that succeeded, however modestly, paved the way for the future. As multicellularity flickered into existence, the conditions of Earth still held life in check. The oceans remained stratified, nutrients limited, and oxygen confined to narrow bands. Complexity had appeared, but it waited in silence, constrained by the environment. The experiments would continue, shaping possibilities, holding their ground until the world itself shifted to allow them room to grow. From these faint beginnings, the story moves outward to the grander stage of the planet itself. While life tested its first steps toward complexity, the continents above were not still. They were drifting, merging, and reshaping the Earth's surface, preparing new environments that would influence the course of evolution in ways as profound as the biology of the cells themselves. While life in the oceans was quietly experimenting with new forms of complexity, the surface of the Earth itself was shifting on a scale both vast and profound. Continents, which had once floated apart as scattered fragments, were beginning to drift together, locking into a configuration that would shape climates, seas, and the flow of nutrients for hundreds of millions of years. Geologists call this immense landmass Columbia, also known by the name Nuna, and it is considered one of the earliest true supercontinents. To understand how Columbia came to be, it helps to picture the foundations of the continents, called cratons. These are ancient pieces of crust, built in the deep past, stable and enduring compared to the younger rocks that surround them. Over time, cratons slowly collided, driven by the motion of Earth's tectonic plates. They fused along mountain belts, forming the skeleton of a continent that stretched across much of the globe. By about 1.5 billion years ago, Columbia had assembled into a single giant landmass, linking regions that today are scattered across many modern continents. Parts of North America, South America, India, Australia, and China once sat together, bound as neighbors in this ancient supercontinent. The formation of Columbia was not a sudden event, but a long and patient process. Over hundreds of millions of years, mountain ranges rose where cratons collided, only to be worn down by weather and time. Rivers carried sediments across vast interiors, spreading minerals into shallow seas. Volcanoes erupted along continental edges, releasing gases and ash into the atmosphere. The cycles of uplift, erosion, and deposition shaped not only the face of the land, but also the chemistry of the oceans that hugged its coasts. Supercontinents matter deeply to life, even in ages where visible complexity was limited. The sheer size of Columbia influenced the flow of winds and the circulation of currents, stabilizing climates across wide regions. Its great interior was dry and weathered slowly, while its edges delivered nutrients like phosphorus and iron into the oceans. These nutrients, though scarce, were essential for the photosynthetic microbes that produced oxygen. Each river that drained the continent became a conveyor belt, carrying the ingredients of life into shallow seas where microbial mats flourished. The arrangement of land masses also affected carbon dioxide levels, one of the key regulators of Earth's temperature. As mountains rose and crumbled, their minerals reacted with the air, drawing down carbon dioxide and storing it in rocks. This process cooled the climate gradually, balancing the warmth of the ancient sunlight. Without these geological feedbacks, Earth's environment might have tipped into extremes that life could not endure. Instead, the slow breathing of Columbia's mountains and rivers provided stability. Columbia also set the stage for cycles that would continue throughout Earth's history. Supercontinents do not last forever. They gather, break apart, and then come together again in new forms. Each cycle reshuffles the surface of the Earth, reorganizing habitats, redirecting ocean currents, and altering the delivery of nutrients. These changes ripple through the biosphere, influencing the pace and direction of evolution. Columbia was one of the earliest examples of this grand rhythm, and in its time, it shaped the possibilities of life in ways that we are only beginning to understand. Imagine the world as it might have appeared then, a single continent stretched across much of the globe, its vast interior barren and rocky, while along its coasts shallow seas shimmered with microbial life. The skies carried volcanic haze from eruptions at its edges, and mountain ranges rose and fell as tectonic forces continued to mold the land. Though life remained small and hidden, the planet itself was laying down the structures that would guide the future. As Columbia slowly shifted and evolved, it set in motion patterns that would one day lead to its own fragmentation and the birth of new supercontinents. And with each tectonic change came subtle influences on the oceans and the atmosphere, shaping conditions that life would either endure or seize upon. From Columbia's long presence, the story moves forward to its successor, a new continental arrangement that rose from its breaking, known as Rodinia. As the long reign of Columbia slowly drew to a close, the restless motion of Earth's plates began to pull the ancient supercontinent apart. For hundreds of millions of years, its vast landmass had anchored climates and delivered nutrients into shallow seas. Yet no supercontinent lasts forever. The same tectonic forces that build mountains and fuse cratons together eventually tug them apart, splitting interiors and opening new oceans. It is a cycle written deep into the planet's crust, and Columbia was no exception. The breakup began with rifting, as molten rock pushed upward from the mantle, stretching and thinning the crust until fractures split open across the supercontinent's body. These fractures widened slowly, filled with magma that cooled into new oceanic crust. Valleys deepened into seas, and coasts that had once been joined began to drift away from one another. In some places, mountains that had formed during Columbia's assembly were eroded to low hills, while elsewhere, new volcanoes rose along fault lines, spilling lava into widening basins. Over time, This slow and relentless movement gave rise to Rodinia, the next great supercontinent. By roughly 1 billion years ago, the scattered fragments of Columbia had reorganized into a new configuration, bringing together land masses that would one day form parts of North America, South America, Africa, Australia, and Antarctica. The shape of Rodinia was different from Columbia, with large blocks gathered toward the equator, surrounded by wide and newly formed oceans. This fresh arrangement once again altered the balance of winds, currents, and climates across the globe. The oceans themselves were reshaped in profound ways. As land masses drifted apart and reassembled, ocean basins opened and closed, redirecting circulation patterns. Waters that had once been confined by Columbia's broad coasts now flowed into new spaces, mixing differently, carrying nutrients and gases in unfamiliar paths. Though life remained mostly microbial, these shifts mattered deeply. Where continents eroded, rivers poured phosphorus and other elements into shallow seas, offering resources that microbial mats depended upon. Where tectonic activity lifted mountains, weathering drew down carbon dioxide, influencing the delicate balance of global temperature. Rodinia's rise also meant new volcanic arcs and rift valleys, each releasing gases into the atmosphere. These emissions, combined with the drawdown of carbon dioxide from weathering, helped regulate climate, preventing extremes that could have frozen the planet or overheated the seas. The world of the Boring Billion was defined not by drama, but by this slow choreography of balance, shaped as much by drifting continents as by the microbes that coated their shores. It is striking to imagine the Earth of this time. Rodinia spread across the globe, its broad interiors barren and dry, its coasts lined with shallow waters rich in microbial life. The skies were hazy with volcanic gases, and vast stretches of ocean stretched out, dark and layered, carrying limited oxygen near the surface and poison in the depths. The land was empty of trees or grasses, the continents silent save for wind and rain. Yet beneath this apparent stillness, Earth's tectonic heart was alive, guiding the rhythms of climate and chemistry in ways that would set the stage for everything to come. Rodinia's assembly was not the end of motion, but another chapter in a continuous cycle. Supercontinents gather and break apart in a rhythm that spans hundreds of millions of years. Each time they assemble, they influence climate stability and nutrient flow. Each time they split, they create new coasts, fresh habitats, and shifting oceans that alter the conditions for life. Rodinia was the next step in this rhythm, a giant puzzle of drifting plates that shaped the environment during one of the most subdued, yet quietly important, intervals in Earth's history. As Rodinia settled into place, the volcanic activity and continental rearrangements ensured that gases and minerals continued to cycle between the deep earth, the oceans, and the atmosphere. These exchanges maintained the fragile balance of oxygen and nutrients, allowing microbial ecosystems to endure. Yet the restless surface of the planet also carried with it a reminder that balance is never permanent. The rise of Rodinia was followed by its eventual fragmentation, a breakup that would trigger profound changes in climate and chemistry. From this slow tectonic ballet, the story shifts upward to the atmosphere itself. Above the continents and seas of Rodinia, the skies were shaped not only by drifting landmasses, but also by the pulsing of volcanoes, the thin warmth of the sunlight, and the delicate balance of greenhouse gases that kept the Earth from freezing under its ancient star. As Rodinia spread across the globe, the land was far from silent. Along its edges and across its rift valleys, volcanoes burned with steady force. Eruptions were not rare. They were part of the natural rhythm of the planet, a reminder that beneath the crust, the mantle was always in motion. Magma surged upward through cracks, spilling onto the surface as molten rock and spreading across the landscape in dark, glowing floods. The eruptions often left behind vast lava plains, stretches of black basalt that cooled into hard stone. These plains reshaped the environments around them. Rivers were diverted, coastlines altered, and shallow seas sometimes smothered beneath advancing flows. In time, weather and rain broke down these new rocks, releasing minerals that washed into the oceans. These minerals included phosphorus and iron, nutrients that could feed the microbial mats clinging to shallow shores. Though the eruptions themselves were destructive, their aftermath carried gifts, seeding the seas with the ingredients of life. Volcanoes also breathed into the skies. Each eruption filled the air with gases, including carbon dioxide, sulfur, and water vapor. Carbon dioxide, in particular, played a role that was both delicate and essential. The ancient sun shone fainter than it does today, giving off less warmth. Without the presence of greenhouse gases to trap heat, Earth might have slipped into a frozen state. The release of carbon dioxide from volcanoes acted as a safeguard, building a thin veil of warmth that kept the planet's surface from falling into deep ice. Yet the balance was not simple. Too much volcanic carbon dioxide could have overheated the Earth, while too little would have plunged it into cold. Weathering of the lava plains and mountain ranges pulled carbon dioxide out of the air, locking it into minerals, while eruptions returned it again. In this way, volcanoes and rocks together created a kind of breathing cycle for the planet. The result was a climate that remained relatively stable for hundreds of millions of years, neither boiling nor frozen, but held in a middle ground that allowed microbial life to persist. Volcanic skies were also tinted with ash and aerosols. Eruptions could temporarily dim sunlight, casting hazy veils across the atmosphere. The effects may not have been catastrophic, but they added to the complexity of Earth's climate system, shifting the balance between warmth and coolness in subtle ways. Over the vast span of the boring billion, countless eruptions contributed to this balance, their combined influence woven into the stability that defined the age. Imagine standing on the barren surface of Rodinia, where no forests softened the land and no animals yet walked. From the horizon, fountains of lava rose, glowing against dark skies. Rivers of molten rock flowed until they cooled into stone, their surfaces cracking as they hardened. Ash drifted through the air, carried by winds across empty plains. The land was harsh, but each eruption was part of a grander system, cycling gases and minerals between the deep earth, the atmosphere, and the seas. This endless exchange was vital for the survival of life. Microbes depended on the nutrients washed into coastal waters. Oxygen levels, though low, were sustained in part by the balance between volcanic release and chemical drawdown, and the climate, fragile under a faint young sun, remained habitable thanks to the steady hand of volcanic carbon dioxide. Without these eruptions, the Earth might not have maintained its long equilibrium. Volcanoes are often remembered for their violence, but during the boring billion, they acted more like guardians of balance, keeping Earth warm enough for life to endure. They did not create great dramas of extinction or sudden bursts of abundance. Instead, their patient work sustained the quiet world of microbes, holding conditions steady while life prepared for revolutions yet to come. Above these volcanic landscapes, however, the sun itself was dimmer than it is today, its light weaker by a significant margin, and yet despite this faint glow, the Earth remained unfrozen. The answer lies in the greenhouse gases that volcanoes help sustain, part of the planet's careful balance under the paradox of a dimmer star. High above the shifting continents and volcanic plains of Rodinia, the sun shone with a gentler light than it does today. Scientists estimate that around 1.5 billion years ago, the sun radiated perhaps only three-quarters of its present strength. This is part of what is known as the faint young sun paradox. By all simple calculations, a weaker star should have left Earth frozen solid. Without enough warmth reaching the surface, the planet ought to have been locked in ice, the seas sealed, and life extinguished in silence. Yet the rocks and fossils tell us otherwise. The oceans remained liquid, microbes thrived, and the planet continued in a long, stable equilibrium. The paradox lies in understanding how Earth avoided this icy fate. The answer rests in the delicate balance of greenhouse gases. While the sun was dimmer, the atmosphere carried higher levels of gases that trapped heat. Carbon dioxide, in particular, released by volcanoes and balanced by weathering of rocks, formed a thin thermal blanket that held warmth close to the surface. Without this invisible shield, Earth would not have sustained liquid water, and the story of life might have ended before it began. Other gases also contributed to this warmth. Methane, produced by certain microbes, acted as a powerful greenhouse gas in the ancient atmosphere. Though its levels may have varied, in combination with carbon dioxide, it helped maintain temperatures suitable for liquid oceans. Nitrous oxide and water vapor, though less prominent, added their own subtle roles to the mix. Each gas participated in the careful interplay that kept Earth habitable beneath the weaker rays of its young star. This balance was not a static one. Volcanoes continually exhaled carbon dioxide into the skies, while chemical reactions at the surface slowly pulled it back down into rocks. Too much volcanic activity, and the planet might have grown dangerously warm. Too much weathering, and it could have tipped into glaciation. For millions upon millions of years, Earth walked a narrow path, its climate maintained by the interplay of geological and atmospheric forces. The faint young sun paradox is not merely a puzzle of physics, but a reminder of the precision with which life and planet coexisted. It is striking to imagine standing on Rodinia under this dimmer star. The light would have seemed softer, perhaps tinted slightly redder, casting long shadows across barren landscapes. The skies, filled with volcanic haze and drifting aerosols, may have muted the glow even further, yet the seas still shimmered and the air still held enough warmth to cradle life. The microbes that coated shorelines and mats of cyanobacteria did not need blazing sunlight, only enough energy to continue their slow, steady work. The greenhouse gases not only prevented freezing, but also created stability. With oxygen levels held low and nutrients limited, life was not in danger of rapid change or collapse. Instead, the atmosphere and oceans remained in a prolonged balance, a quiet stage where microbes refined their existence and early eukaryotes carried forward the first experiments in complexity. The faint young sun paradox highlights the fragility of this arrangement, showing how easily the balance could have tipped in the other direction. Yet for nearly 1 billion years, it held. The story of the dimmer sun is not just about survival, but about preparation. By maintaining liquid water and a temperate climate, Earth preserved the possibility of future leaps in evolution. Without the greenhouse gases of that time, the oceans might have frozen and never thawed, erasing the conditions needed for multicellularity. The paradox reminds us that stability, even under a weaker star, was a gift that carried life forward, but balance never lasts forever. While the sun slowly grew brighter across the ages, the chemistry of Earth's atmosphere was also changing. Nitrogen and carbon cycles were stabilizing, laying down patterns that would be essential for the emergence of greater complexity. To follow the story further, we turn from the soft glow of a dimmer sun to the intricate transformations within the air itself, where nitrogen became a cornerstone of the biosphere. While the faint young sunlight cast its weaker light across Rodinia and volcanoes exhaled their steady breath into the skies, another transformation was unfolding, one that took place not in the brilliance of light, but in the chemistry of the air itself. This was the stabilization of Earth's nitrogen cycle, a breakthrough as quiet as it was essential. Without it, the molecules of life could never have achieved their intricate complexity. Nitrogen is one of the most abundant gases in the atmosphere, yet abundance does not always equal accessibility. Most of the nitrogen floating in the air exists as N2, two atoms bound so tightly together that they are nearly impossible for life to use. To transform nitrogen into a form that organisms can incorporate, it must be broken apart and reshaped. This process, known as nitrogen fixation, allowed microbes to build proteins and nucleic acids. Proteins give cells their structures and carry out the tasks of life, while DNA encodes the instructions that allow life to endure. In a very real sense, nitrogen is one of the fundamental building blocks of existence. During the early chapters of Earth's history, the nitrogen cycle was unstable, patchy, and easily disrupted by shifts in oxygen and ocean chemistry. But during the boring billion, the cycle began to settle into a rhythm. Microbes that could fix nitrogen, such as certain cyanobacteria, established themselves in shallow seas, capturing atmospheric nitrogen and converting it into ammonia or other compounds usable by living systems. These compounds were taken up by other microbes, passed along food webs, and eventually returned to the environment when organisms died and decomposed. Step by step, nitrogen began to move in a loop, cycling from air to life and back again, establishing one of the most important biochemical circuits on the planet. Evidence of this ancient shift does not come in the form of obvious fossils, but in subtle chemical signatures locked in stone. Geologists studying shales and sediments from more than 1 billion years ago have found patterns in nitrogen isotopes, the slight variations in the atomic weight of nitrogen atoms. These patterns suggest that biological fixation was already widespread and that the nitrogen cycle had begun to resemble something closer to what we know today. Each tiny isotope ratio is like a fingerprint, a quiet testimony that the cycle of nitrogen was in motion, linking air, water, and life. The stabilization of the nitrogen cycle was a hidden revolution. Without a reliable flow of nitrogen, cells could not expand their genetic toolkits. DNA requires nitrogen to form its base pairs, the letters of the genetic code. Proteins, which are made of amino acids, also depend on nitrogen to function. The enzymes that power metabolism, the scaffolds that give cells their shape, and the channels that transport nutrients are all built upon nitrogen. For early eukaryotes and the first multicellular experiments, this steady supply was crucial. Imagine a world without it. Cells would have remained constrained, limited in size and complexity, unable to explore the possibilities of division of labor or cooperation. The quiet stability of nitrogen cycling allowed genetic diversity to flourish, giving evolution the raw material it needed to prepare for the explosions of life that lay ahead. The nitrogen breakthrough also tied into the larger cycles of the planet. As microbes fixed nitrogen, they influenced the productivity of ecosystems, which in turn affected the levels of oxygen in the atmosphere. More nitrogen meant more photosynthesis, more biomass, and more oxygen release, though still confined to low levels during the boring billion. The interplay between nitrogen and oxygen created a delicate feedback that shaped Earth's long equilibrium. This chemical revolution is easy to overlook because it did not leave towering stromatolites or spectacular fossils, but it may be one of the most important steps in Earth's history. Within the quiet isotopes of ancient rocks lies the record of a planet preparing itself for complexity. As nitrogen settled into its reliable rhythm, another element remained in short supply. Life had begun to secure proteins and DNA, but the fuel to power rapid growth was still limited. In the oceans, phosphorus was scarce, throttling the pace of innovation. And so the story of life moves from nitrogen's breakthrough to the puzzle of phosphorus, the element that would determine how far evolution could go in these ancient seas. As nitrogen found its rhythm and began to cycle steadily through the atmosphere and oceans, another element held life in check. It was phosphorus, a nutrient far less abundant than nitrogen, yet just as essential for building the machinery of cells. Without phosphorus, there can be no DNA, no membranes to encase a cell, and no energy molecules such as ATP, which every living thing uses as a battery. Phosphorus is the spark that fuels growth and reproduction, and in the Proterozoic oceans, it was in desperately short supply. The scarcity of phosphorus in ancient seas was not a small inconvenience. It shaped the pace of evolution for nearly 1 billion years. While eukaryotes had appeared and sexual reproduction had begun, the energy required for rapid diversification was throttled. Life remained small and microbial, confined to mats and colonies, rather than spreading into vast, complex ecosystems. Phosphorus scarcity was like a hand on the brake, slowing the unfolding of possibilities that were otherwise ready to bloom. Geology offers clues to why phosphorus was so limited during this time. Much of it was locked away in rocks, bound into minerals that resisted weathering. The supercontinent Rodinia, with its broad interiors and relatively stable climates, delivered fewer rivers and floods to wash phosphorus into the oceans. Where phosphorus did enter the seas, it often sank quickly into sediments, pulled out of circulation before it could fuel long-term productivity. The deep oceans, poor in oxygen and rich in sulfides, also acted as traps, binding phosphorus into minerals and burying it on the seafloor. The evidence of this scarcity is written into the chemical signatures of ancient shales. These rocks, formed from fine mud that settled in quiet waters, preserve a record of nutrient conditions over geological time. Analyses of shales from the Proterozoic reveal unusually low phosphorus to iron ratios, suggesting that much of the available phosphorus was stripped from the water and buried before it could be cycled back into life. Each layer of shale tells the same story: oceans starved of the very nutrient that could have propelled evolution forward. Phosphorus limitation did not halt life, but it constrained it. Microbial mats continued to dominate shallow waters, stromatolites rose patiently from coastlines, and eukaryotes persisted in small colonies. The machinery of complexity existed, but without abundant phosphorus to power rapid growth, these early experiments could not spread widely. Life endured, but it did so in a low gear, waiting for conditions to change. It is sobering to think how much difference a single element made. Without phosphorus, DNA replication slowed, energy cycles lagged, cells could not expand into new roles or support larger, multicellular bodies. The potential for innovation remained bottled up, like seeds lying dormant in dry soil, waiting for rain. The Earth's biosphere was alive, but its dynamism was muted by chemical scarcity. Yet the phosphorus puzzle also points to the resilience of life. Even in nutrient-poor seas, microbes found ways to persist. Some evolved strategies to recycle phosphorus from decaying material, while others tapped into scarce supplies with remarkable efficiency. These adaptations kept ecosystems functioning at a small scale, maintaining the slow equilibrium of the boring billion. The eventual release of phosphorus into the oceans would change everything. Tectonic shifts, mountain building, and erosion in later ages would deliver new supplies of the nutrient, fueling explosions of productivity and paving the way for animals. But during the Proterozoic, the scarcity held, shaping the quiet, drawn-out pace of evolution. From the stillness of nutrient-starved seas, the story of the boring billion continues into the dominance of microbes themselves. Stromatolites and mats remained the architects of shallow waters, building and rebuilding ecosystems in a world where larger organisms had not yet found their foothold. In the nutrient-starved seas of the Proterozoic, where phosphorus was scarce and oxygen remained low, one form of life rose quietly to shape the landscapes of the shallow oceans. These were the microbes, the patient architects of early Earth, whose slow and steady work defined the character of the boring billion. With no plants to root the coasts, no animals to graze the seafloor, and no forest to shade the land, the planet belonged to them. The most striking monuments of their rule were stromatolites. These layered structures grew in shallow waters, where sunlight reached the seabed. Layer upon layer of microbes, often dominated by cyanobacteria, trapped and bound sediments, building up dome-like mounds that rose millimeter by millimeter over centuries. From afar, a Proterozoic coastline might have been dotted with these forms, reef-like ridges spreading in clusters across tidal flats and lagoons. Some grew into large domes taller than a human, silent fortresses built not of stone alone, but of living communities stacked upon themselves. These stromatolites were not lifeless rocks, but thriving ecosystems. At the surface, photosynthetic microbes captured sunlight, releasing oxygen as a byproduct. Beneath them, other microbes consumed waste, cycled nutrients, and created conditions that sustained the layers above. Each dome was a miniature world, a vertical community where life arranged itself by function and need. Though their growth was glacially slow, their influence was immense. They helped shape coastlines, stabilize sediments, and altered the chemistry of the waters around them. Beyond stromatolites, microbial mats spread across wide areas of the seafloor, coating it in flexible, rubbery sheets of life. These mats extended for miles, undisturbed by grazers, since animals had not yet evolved to feed upon them. They acted as living carpets, absorbing nutrients where they could and producing oxygen that seeped into the waters. Some microbes within the mats fixed nitrogen, others broke down organic matter, and still others carried out reactions involving sulfur and iron. Together, they maintained a delicate but powerful balance, slowly constructing the biochemical systems that would one day support more complex life. The dominance of microbes meant that the pace of change was slow but steady. Over millions of years, they cycled elements through the oceans and atmosphere, adjusting the levels of oxygen, nitrogen, carbon, and sulfur. They were the unseen engineers of Earth's biogeochemistry, working not in dramatic bursts but through persistence. Each mat, each stromatolite, was a participant in this grand construction, shaping a planet that would eventually be ready for animals. Evidence of their reign is preserved in the rocks of this age. Stromatolites are abundant in Proterozoic formations, more common than in any later period of Earth's history. Their fossils appear as layered columns and domes, cross-sections of microbial patients carved into stone. Chemical traces within these rocks reveal how mats altered local environments, drawing in nutrients and creating distinct signatures of oxygen and carbon. Even today, living stromatolites can be found in a few rare places, such as Shark Bay in Australia, where modern microbes continue the same slow work as their ancient ancestors. The scale of their dominance is difficult to imagine. For hundreds of millions of years, stromatolites and microbial mats were the most visible forms of life on the planet. They filled shallow seas, colonized lagoons, and spread across tidal flats. No trees shaded the land above them, no fish disturbed the waters, no predators grazed upon their layers. In this vast stillness, microbes reigned unchallenged, their quiet labor shaping Earth into a world that could one day support forests, reefs, and animals. The story of microbial dominance is not one of stagnation, but of construction. While the surface world seemed monotonous, these communities were engineering the foundations of modern ecosystems. They maintained stability, buffered the atmosphere, and recycled nutrients, preparing the way for the future. Without them, the later explosion of complexity could never have occurred. And while microbes patiently ruled the shallow seas, the planet itself was offering them protection. Deep within the core, forces were at work that shielded life from the harshness of the sunlight. As microbes spread across coasts and tidal flats, Earth's magnetic field strengthened, building an invisible barrier that preserved the fragile balance of survival. While microbial mats spread across shallow seas and stromatolites built their layered domes, the planet itself was undergoing a transformation deep within its core. This change was invisible on the surface, yet it was one of the most important shifts in Earth's history. The molten heart of the planet was stirring, and with its movement came the strengthening of a force that would protect life for billions of years to come. This was the birth of Earth's magnetic shield. At the center of the planet lies a solid inner core of iron, surrounded by a liquid outer core also rich in iron and nickel. As the inner core began to crystallize more than 1 billion years ago, it released heat and caused the liquid metal around it to churn. This movement created powerful currents that acted like a planetary dynamo, generating a magnetic field that stretched far beyond Earth's surface. The field was not visible to the eye, but it extended outward into space, forming a protective bubble known as the magnetosphere. Without this magnetic shield, the solar wind would have stripped away Earth's atmosphere. The sun continuously sends out a stream of charged particles, racing through space at tremendous speeds. For a planet without protection, this wind can erode gases, breaking apart molecules and sending them drifting into space. Mars offers a haunting example. Once it may have had thicker air and flowing water, but without a strong magnetic field, its atmosphere was gradually lost, leaving behind a barren and frozen world. Earth avoided this fate because its magnetic field stood as a barrier, deflecting the solar wind and preserving the delicate envelope of gases that life required. The shield also protected life from harmful radiation. The sun's charged particles, if left unchecked, would have bombarded the surface with energy too intense for fragile organisms. But within the magnetosphere, these particles were steered away, guided toward the poles where they created shimmering auroras. Even in the Proterozoic skies, long before animals looked upward, the northern and southern lights must have danced across the heavens, a luminous reminder of the invisible guardian at work. The strengthening of Earth's magnetic field during the Boring Billion provided more than just safety. It ensured that the balance of gases in the atmosphere, including oxygen and carbon dioxide, could be maintained over vast timescales. This stability gave microbes the conditions they needed to persist and refine their biochemistry. Without the magnetic shield, the oxygen released by cyanobacteria might have been lost to space, and the slow rise of complexity in eukaryotes might never have had the chance to unfold. Though life at the time was too simple to perceive the shield, every organism benefited from its presence. Each stromatolite, each filament of red algae, each drifting eukaryote survived beneath its protection. The magnetic field was silent, invisible, and unrecognized, yet it was one of the most powerful allies life has ever had. Geological records give us subtle hints of its existence. Ancient rocks contain tiny crystals of magnetite, aligned like compass needles, preserving the direction of Earth's magnetic field at the time they formed. From these minerals, scientists can trace the history of the field, noting that it grew stronger during the Proterozoic. These tiny alignments, frozen in stone, are whispers from a time when Earth's invisible guardian was first stretching its shield across the planet. The magnetic field's influence reached far beyond protection. By preserving the atmosphere, it helped regulate climate and allowed the greenhouse gases from volcanoes to work in harmony with the faint young Sunday. It was part of a larger system, linking the deep earth to the skies above, ensuring that the fragile balance of habitability endured. As this invisible barrier wrapped the planet in its protection, life continued to flow through its patient rhythms. The oceans, still low in oxygen, cycled nutrients slowly, guided by currents that moved to the subtle beat of Earth's rotation and tilt. This long stability left its mark in the carbon records of the time, a planetary heartbeat that can still be read in the rocks today. With Earth's magnetic shield guarding the atmosphere and life continuing its patient work in the oceans, the planet itself began to settle into patterns of stability that stretched across unimaginable spans of time. The boring billion is often described as uneventful, but this long stillness can also be seen as a rhythm, a steady pulse that kept Earth habitable. The evidence of this rhythm is preserved in the chemistry of ancient rocks, where the carbon cycle left its quiet signature. The carbon cycle is one of the great regulators of climate. Carbon moves between the air, the oceans, the biosphere, and the rocks beneath our feet. Volcanic eruptions release carbon dioxide into the atmosphere. Rain and weathering draw it back down into minerals. Organisms use carbon to build their bodies, and when they die, much of it returns to sediments or to the seas. Over millions of years, this constant exchange forms a feedback system, one that smooths out extremes and holds the planet within a narrow band of stability. During the Proterozoic, geologists find that this cycle left an unusually calm record. In carbon isotopes preserved within shales and carbonates, the ratios show only gentle swings, lacking the sharp spikes and drops that characterize later ages of glaciations and extinctions. It is as if the planet was breathing slowly, inhaling and exhaling carbon in a rhythm too even to be called dramatic, but steady enough to carry life through nearly a billion years. These early climate rhythms did not produce catastrophic change. There were no massive die-offs, no sudden plunges into snowball states, no rapid spikes of warming. Instead, Earth seemed to drift within a balance, the faint sunlight, the greenhouse gases steady, and the oceans quietly stratified. This stability was both a limitation and a gift. It held back the rise of animals that required higher oxygen and faster nutrient cycles, but it also prevented disasters that might have wiped out the delicate microbial ecosystems. Imagine a world where seasons came and went with little drama, where ocean currents moved without drastic upheavals, and where volcanic emissions and rock weathering balanced each other across tens of millions of years. It was not a planet asleep, but a planet maintaining a calm equilibrium. In this quiet, microbes built stromatolites, eukaryotes refined their internal machinery, and the genetic toolkit for complexity slowly assembled itself, waiting for the right moment. The concept of Earth's long planetary heartbeat comes from these records. The rocks suggest cycles of stability, repeating over and over, like a pulse measured in millions of years. Some scientists believe this stability was linked to the position of Rodinia, the supercontinent, whose great size influenced ocean currents and weathering rates. Others point to the carbon cycle itself, acting as a thermostat, keeping climate within bounds despite the faint sunlight. Whatever the mechanism, the rhythm was real, and it gave the boring billion its characteristic stillness. This stability is fascinating because it shows how a planet can remain habitable even without great bursts of change. On worlds beyond our own, exoplanets circling faint stars might also hide such long, uneventful ages where microbial life endures quietly beneath calm skies. The lesson of Earth's early heartbeat is that stillness does not mean emptiness. Even in ages of apparent monotony, the foundations for future revolutions can be laid. As the Proterozoic wore on, the rhythm continued, a long inhale and exhale of carbon that gave the planet its steady pulse. But within this calm, genetic clocks hint at hidden stories, suggesting that animals may have already been stirring in ways too small for the fossil record to capture. These invisible ancestors remind us that beneath the stability, life was preparing for the moment when change would finally break through. Through the long stability of the Proterozoic, the oceans seemed to belong only to microbes and simple eukaryotic cells. Stromatolites rose patiently, microbial mats stretched across the seafloor, and red algae flickered as delicate filaments in shallow waters. To the fossil record, it appears as if animals were absent, their arrival delayed until nearly 600 million years ago. Yet genetic studies suggest a quieter possibility, one that reshapes how we see this silent chapter. According to the ticking of molecular clocks, animals may have already existed, hidden in forms too fragile to leave behind a record. A genetic clock is built by comparing the DNA of living organisms. Mutations occur at roughly predictable rates, and by measuring these changes, scientists can estimate when different groups diverged from common ancestors. When applied to the history of animals, these clocks point to origins far earlier than the first fossils. Some estimates suggest that simple animal lineages may have begun more than 800 million years ago, deep within the boring billion itself. If animals were already present, why do the rocks remain silent? Part of the answer lies in the nature of those first creatures. They may have been microscopic, small colonies of cells that left no shells or bones to fossilize. Their bodies would have been soft and ephemeral, dissolving quickly after death. Even if they survived long enough to be buried, the chemistry of Proterozoic sediments was not always favorable for preservation. Without hard parts, without size, and without mineralized tissues, they slipped through the filter of the fossil record, leaving only genetic echoes behind. Some scientists call this the hidden ancestors hypothesis. It suggests that animal life may have begun quietly, invisible to our tools, occupying niches in microbial mats or drifting in planktonic layers of the sea. Perhaps they grazed on bacteria, altering ecosystems in subtle ways. Perhaps they formed tiny colonies, precursors to sponges or other simple lineages. If they existed, they were not yet abundant enough to transform the biosphere, but they were present, shaping possibilities in ways we can only infer. The lack of direct fossils does not mean the story is empty. Indirect evidence sometimes peeks through. Chemical traces called biomarkers, preserved in ancient sediments, hint at molecules associated with sponge-like organisms. Though these traces are debated, they open the possibility that the first animals were already filtering seawater hundreds of millions of years before the Cambrian explosion. The genetic clocks, the biomarkers, and the faint hints in isotopic data weave together a picture of life that was more complex than the rocks suggest. Imagine these hidden ancestors moving silently through nutrient-starved seas. They were small, soft, and vulnerable, but they carried within them the blueprint for all future animals, the capacity for multicellularity, the ability to coordinate cells into tissues, the beginnings of nervous systems and muscles, all may have been seeded in this quiet interval. These lineages may have flickered in and out of existence, surviving in pockets where oxygen was sufficient, only to vanish when conditions shifted. The fossil record misses them, but the molecules within our own DNA remember. This long wait for animals is both haunting and beautiful. It is a reminder that absence in the rocks does not mean absence in reality. Evolution often works in shadows, shaping possibilities before they burst into visibility. For nearly 1 billion years, Earth held its breath, supporting simple life on the surface, while the seeds of animals germinated invisibly. As the Proterozoic drew toward its end, subtle changes began to gather momentum. Rodinia started to fracture, oxygen levels in the atmosphere crept upward, and nutrients flowed more freely into the seas. The hidden ancestors, if they truly existed, were poised to take advantage. Their long invisibility was nearing its end. Soon the calm stability of the boring billion would give way to disruptions, and with them, the first undeniable traces of animals would emerge. For nearly 1 billion years, Earth's climate held steady, a long plateau of calm that allowed microbes to dominate the seas and quiet experiments in complexity to unfold. Yet stability never lasts forever. Deep in the geochemical record, hidden within the ratios of carbon and oxygen locked in ancient rocks, there are hints that this calm was beginning to fray. Subtle shifts in the chemistry of sediments point to changes brewing in the balance of the atmosphere and oceans. These were the faint signals, the precursors of the great ice ages that would eventually transform the planet into a frozen sphere. The first clues come from the way carbon moved through Earth's systems. For much of the boring billion, carbon isotopes in marine rocks had remained remarkably steady, a sign of balance between volcanic release, biological uptake, and burial in sediments. But as the Proterozoic drew to a close, the record began to show disturbances. Periodic excursions in the carbon cycle suggest that the long equilibrium was breaking. At times, more carbon dioxide seemed to be pulled out of the air and stored in rocks, tipping the climate toward cooling. Other geochemical markers tell similar stories. Sulfur isotopes hint at fluctuations in oxygen and nutrient cycles, signs that the oceans were no longer as chemically stable as before. Iron formations reappeared in certain layers, suggesting shifts in oxygenation that affected deep waters. Together, these signals suggest a planet entering a new phase of dynamism, its atmosphere and seas no longer locked in the same predictable rhythm. The reasons for this change are written in the slow dance of continents. Rodinia, which had gathered as a supercontinent, began to break apart around 800 million years ago. Rifting open new coastlines, increasing the weathering of rocks. As rivers carried minerals into the seas, phosphorus availability may have risen, boosting productivity of photosynthetic microbes. More productivity meant more oxygen release, but also more burial of carbon in sediments. Each burial event drew carbon dioxide from the air, weakening the greenhouse effect and allowing the planet to cool. The tectonic shifts that fractured Rodinia planted seeds of instability in the climate system. Volcanoes, too, played a part. While they continued to exhale carbon dioxide, their contributions sometimes could not keep pace with the rate at which carbon was being locked into rocks. This imbalance tilted the scales toward cooling. Even slight reductions in greenhouse gases, combined with a sunlight still fainter than today, could nudge Earth toward ice. What makes these precursors so haunting is how small shifts could cascade into global transformations. A few million years of enhanced weathering, a modest increase in nutrient flow, or a slight drawdown of carbon dioxide might be enough to trigger runaway feedbacks. As ice sheets began to grow in polar regions, their white surfaces reflected more sunlight, amplifying cooling further. Once this feedback loop began, it could drive the entire planet into a snowball state. The Neoproterozoic ice ages were not yet upon Earth during the late Proterozoic, but their seeds were already sown. The rocks of this time preserve the whispers of change, chemical patterns that foreshadow the catastrophes to come. It is as if the planet, after a billion years of steady breathing, was beginning to draw a deeper, colder breath. In this way, the boring billion was both an age of stability and the staging ground for upheaval. The calm rhythms of the carbon cycle began to falter. Tectonic shifts broke apart old patterns, and the atmosphere itself edged closer to thresholds it could not easily retreat from. Life, still microbial and modest, endured these subtle shifts, unaware that it was drifting toward one of the most severe challenges it would ever face. As the precursors of Snowball Earth gathered, the quiet world prepared unknowingly for its trial. Soon the balance would tip, and the planet would plunge into an icy prison that stretched from pole to equator. But before the great freeze arrived, the calm age of the Proterozoic would reach its final centuries, a time when the first clear signs of transition became unmistakable. For nearly a billion years, Earth had been steady, its climate calm, its oceans restrained, and its life simple. But around 800 million years ago, the rhythm of this long stillness began to change. The planet that had drifted in balance for so long was entering a period of transition. Subtle at first, then increasingly dramatic, the marks of change can be traced in the rocks and chemical signatures of this time. The boring billion was drawing to a close, and the world was preparing for upheaval. The breaking of Rodinia lay at the heart of this transformation. For hundreds of millions of years, the supercontinent had held much of Earth's land together, its presence shaping climate, ocean currents, and nutrient flows. But tectonic forces never rest. Beneath the crust, the mantle was churning, and fractures began to pull Rodinia apart. What had once been a single landmass began to split into smaller continents, drifting slowly across the globe. The breakup of Rodinia created new coastlines, reshaped ocean basins, and set in motion changes that would ripple through the atmosphere and biosphere alike. With the opening of new rifts came rivers and erosion, delivering fresh nutrients into the oceans. Phosphorus and other vital elements, once scarce, began to flow more freely. In shallow waters, photosynthetic microbes took advantage of the new abundance, multiplying rapidly and releasing more oxygen into the atmosphere. For the first time in hundreds of millions of years, oxygen levels began to rise beyond their long plateau. This shift was not sudden, but it was significant. It hinted at a world preparing itself for greater complexity, a world where animals could one day thrive. Yet abundance also brought instability. When nutrients flooded into coastal seas, microbes bloomed in large numbers. As they died and decayed, they consumed oxygen from the water, creating areas of anoxia that spread across the seafloor. These oxygen-poor zones destabilized ecosystems and altered chemical balances. The cycles that had once kept the oceans in equilibrium now began to fluctuate, sometimes swinging toward oxygenation, sometimes tipping back into suffocation. The steady rhythm of the boring billion was breaking, replaced by pulses of change. This period also saw carbon dioxide levels fluctuate as volcanic outgassing and weathering of newly exposed rocks fell out of balance. The greenhouse effect that had kept the planet warm beneath a fainter sunlight now wavered, making Earth more vulnerable to swings in climate. Cooling events began to appear in the geological record, precursors to the glaciations that would later grip the world. The long calm of the Proterozoic was giving way to volatility. The rise in oxygen during this time is one of the most profound shifts in Earth's history. Known as the Neoproterozoic oxygenation event, it marked the beginning of conditions suitable for larger, more complex organisms. While the fossil record still shows mostly microbial life, genetic evidence suggests that animals may have already been waiting in the wings, ready to expand as oxygen allowed. The end of quiet created the stage on which these hidden ancestors could finally emerge into visibility. It is striking to imagine the Earth of 800 million years ago. The continents, once bound together, were now drifting apart, their coastlines etched by new seas. Rivers carried minerals into the oceans, where blooms of microscopic life altered the chemistry of the waters. Oxygen levels in the air crept upward, invisible but transformative. The skies themselves may have looked unchanged, but the air was slowly becoming more breathable, laying the groundwork for creatures far larger and more active than microbes. The end of the boring billion was not a single moment, but a transition spread across millions of years, a long unraveling of stability that gave way to change. What had been calm seas and patient cycles became more dynamic, more unstable, but also more full of possibility. From this instability would come both crisis and opportunity, as Earth moved toward the great ice ages of the Neoproterozoic and, eventually, toward the Cambrian explosion of life. The world was shifting, and with it, the destiny of life itself. From the breakup of Rodinia to the rise of oxygen, the end of quiet set in motion the revolutions that would define the next chapter in Earth's story. As Rodinia fractured and oxygen began to rise once more, the stage was being set for one of the most dramatic chapters in the history of life. Yet the coming boom of diversity did not appear suddenly out of nothing. It was built upon the long foundation of the boring billion, that billion-year stretch of patience in which life quietly assembled the tools it would later unleash. The Cambrian explosion, with its dazzling array of animals, could only occur because evolution had been preparing in the shadows for hundreds of millions of years. Inside the cells of eukaryotes, the genetic toolkits for complexity were already in place. Genes that controlled how cells divided, communicated, and specialized had been evolving during the stillness of the Proterozoic. These genes formed what scientists sometimes call developmental toolkits, the molecular instructions that allow cells to form tissues and tissues to form bodies. Without them, the sudden rise of animals in the Cambrian would have been impossible. The quiet billion years were not wasted time, but a laboratory in which evolution refined the building blocks of complexity. Sexual reproduction, which had emerged earlier in the Proterozoic, played a vital role in this preparation. By mixing genetic material, it generated variation more quickly than simple cell division ever could. Over millions of years, this reshuffling allowed lineages to accumulate innovations, storing them like seeds waiting for the right conditions. When oxygen levels rose and nutrients became more available, these seeds were ready to germinate in bursts of new forms. Even multicellularity, though limited during the boring billion, was being tested. Red algae and possible sponge-like organisms hinted that life had already begun experimenting with ways to organize cells into larger bodies. These experiments did not flourish widely under the nutrient-poor, low-oxygen conditions of the time, but they planted the idea of cooperation. By the end of the Proterozoic, the genetic instructions for multicellular organization were embedded in the DNA of many organisms, ready to be expressed fully when the environment allowed. The fossil record of this preparation is sparse, but molecular evidence adds weight to the story. Genes found in modern animals trace their origins back to this quiet interval long before the Cambrian. They include the instructions for building muscles, nerves, and complex body plans. It is as if evolution wrote the first draft of animals during the Proterozoic, but held it in reserve, waiting for the world to catch up. This waiting was not meaningless. The billion years of stability gave life the time it needed to refine complexity slowly, without being erased by catastrophic upheavals. If the Earth had been more unstable during that stretch, with frequent mass extinctions or dramatic climate shifts, many of these genetic innovations might have been lost before they could take hold. Instead, the long calm preserved them, storing possibilities that would later burst into reality. Imagine the oceans in those final chapters of the Proterozoic. To the eye, they would still appear simple, filled with mats of microbes and faint traces of red algae. But within the genetic material of these organisms lay the codes for nerves that would one day sense light, muscles that would one day swim, and skeletons that would one day anchor bodies. The seas were not empty, but pregnant with possibility, a library of instructions waiting to be read. The Cambrian explosion is often described as life's great fireworks display, but its sparks were struck long before the boom began. The quiet billion years were the fuse, burning slowly, gathering potential, and aligning conditions. Without this stretch of patience, the sudden rise of animals would never have been possible. As Earth approached the end of the Proterozoic, the stage was finally set. Oxygen levels were climbing, nutrients were becoming more available, and genetic toolkits were ready. Soon, the stability that had lasted so long would shatter completely, and the first great glaciations of the Neoproterozoic would sweep across the globe. In the icy crucible of snowball Earth, the final tests would take place, pushing life to its limits and preparing it for its leap into dazzling abundance. When scientists first named this vast span of Earth's history the boring billion, it was meant as shorthand for its apparent lack of drama. No mass extinctions scar the record, no towering forests rise or fall, no sudden bursts of new animals stride onto the stage. At first glance, it seems like a lull in the story, a long pause in the music of evolution. Yet when we look more closely, the lesson becomes clear. Stability is not emptiness. It is as important for life as chaos, perhaps even more so. Evolution thrives, not only in the wake of catastrophes, but also in the calm stretches that allow complexity to accumulate. During the boring billion, life was not reinventing itself with every disruption. Instead, it was refining, experimenting, and quietly solving the problems that would later make animals possible. The invention of sexual reproduction, the stabilization of the nitrogen cycle, the first steps toward multicellularity, and the assembly of genetic toolkits all unfolded in this patient interval. Without the long stability of this billion years, those innovations might never have survived. This idea reveals something profound about habitability. A planet does not need constant drama to support life. In fact, long plateaus may be the best conditions for fostering complexity. Too much upheaval, and life is thrown back to its simplest forms again and again. Too little stability, and genetic innovations cannot take root. The boring billion shows us that a world can thrive by being steady, allowing biology to prepare itself for leaps that only happen when conditions are right. In the rocks, we can trace how this stability worked. The carbon cycle remained in balance for ages, acting like a thermostat to prevent extremes. The magnetic field strengthened, shielding the atmosphere from erosion. Continents shifted slowly, delivering nutrients in modest but steady amounts. Microbes filled the oceans, not in sudden explosions, but in enduring dominance that shaped the chemistry of the world. Together, these quiet forces preserved Earth as a habitable planet, while its stars shone faintly above. These lessons extend beyond our own planet. As astronomers search for life on exoplanets circling distant stars, they often look for signs of dramatic change, sudden oxygen spikes, bursts of activity, or traces of geological upheaval. Yet the boring billion suggests another possibility. A world that looks calm and uneventful might still be nurturing hidden revolutions. On a planet with long stability, microbes may be quietly refining themselves, building the molecular foundations for complexity that has not yet appeared in the fossil or atmospheric record. Imagine a distant world where the skies are hazy, the oceans calm, and the geology unremarkable. To a telescope, it might seem lifeless. Yet beneath those waters, microbial mats could be fixing nitrogen, stabilizing carbon, and laying down the first steps toward multicellularity. It might look boring, but within its stillness lies profound potential. Earth itself tells us that boring does not mean barren. The boring billion teaches us that evolution is not always a race. Sometimes it is a meditation. Just as chaos has its role in shaping bursts of new life, stability creates the conditions where life can gather strength. Both are essential, but stability is often overlooked because it leaves fewer obvious marks in the fossil record. The truth is that the billion-year stillness of the Proterozoic was one of the most creative intervals in Earth's history, not in spectacle, but in preparation. From this recognition, the story moves toward its deeper connections. The forces that erased a billion years of rocks in the Great Unconformity remind us how easily records of stability can vanish. The cycles of the deep Earth, the mantle, and the continents show us how planetary rhythms shape biology, and the first glimpses of diversity, hidden in the smallest of fossils, remind us that even in long quiet stretches, life never stops reaching forward. When we turn to the story of Earth's past, we often imagine it as a book, its pages written in stone. Each layer of sediment seems like a sentence, each fossil like a word, together composing a history that reaches back billions of years. But what makes this book so haunting is how many of its pages are missing. In some places, entire chapters have been torn away. Nowhere is this more striking than in the great unconformities, the silent gaps where a billion years or more of Earth's history has vanished without a trace. An unconformity is what geologists call the surface, where younger rocks lie directly on much older ones, with nothing in between. Imagine walking across a canyon floor and touching one layer of sandstone, only to find that it rests immediately on granite, a billion years older. Where did the missing layers go? The answer lies in the patient forces of tectonics and erosion, which erase as much as they create. Erosion is one of the most powerful editors of Earth's story. Wind, water, and ice grind away at the surface, carrying sediments to rivers and seas. Over millions of years, mountains can wear down completely, their histories washed away grain by grain. Sometimes, erosion strips rocks so thoroughly that whole eras vanish, leaving behind only a flat surface where new layers are later deposited. The time lost to erosion can span hundreds of millions of years, a silence that geologists can only measure indirectly. Tectonic forces add another layer to this puzzle. Continents drift, collide, and break apart. As they move, rocks are buried deep within the crust, where heat and pressure transform them beyond recognition. Sedimentary layers full of history may be metamorphosed into new kinds of stone, their fossils destroyed, their chemical signatures erased. In other cases, tectonic uplift raises ancient rocks to the surface, exposing them to erosion while the younger layers above are stripped away. The combined effect of burial, deformation, and erosion can obliterate vast stretches of geological time. The Great Unconformity, visible at the Grand Canyon and other sites around the world, is the most famous example. In Arizona, it appears as a sharp line where ancient crystalline rocks, more than 1.5 billion years old, are directly overlain by sandstones deposited only about 500 million years ago. Between them, nearly 1 billion years are missing. No fossils, no sediments, no pages of the story remain. This is the geological equivalent of opening a history book and finding that half of it has been ripped away. Yet geologists have ways of piecing together these absences. They read the clues preserved at the edges of the gaps. Minerals within the older rocks may retain chemical signatures that hint at the environment just before the erasure. The younger layers may preserve evidence of what came after, showing how the story resumed. By comparing sites across different continents, geologists can trace where missing time has been preserved elsewhere, stitching together fragments like a quilt of lost ages. Radiometric dating adds another layer of insight. By measuring the decay of isotopes in minerals, scientists can determine the ages of rocks with remarkable precision. When a younger layer rests on an older one with nothing in between, dating reveals the length of time erased. Chemical isotopes of carbon, sulfur, and nitrogen provide further hints, whispering of cycles that continued even when the sediments recording them were removed. The missing rocks remind us that Earth's history is not a perfect archive. It is more like a palimpsest, a manuscript written, erased, and rewritten over and over again. For every fossil we find, there are countless others lost forever. For every layer we study, there are others that were worn away before they could tell their story. The unconformities are both gaps and revelations, showing us the scale of time that can vanish under the forces of geology. These missing chapters matter deeply because it was during the long silence of the Proterozoic that life was quietly preparing for its future revolutions. To find evidence of these hidden stories, scientists must often look beyond the visible rocks into the chemistry of the deep earth, the cycles of mantle convection, and the slow heartbeat of supercontinents rising and falling. When we look at the surface of Earth, we see shifting continents, growing mountains, and rivers cutting their way through stone. Yet all of these changes are only the outermost expression of deeper forces. Beneath our feet, stretching thousands of kilometers down, lies the mantle, a vast layer of hot rock that flows slowly over time. Its movements are not violent in the way we imagine flowing rivers or erupting volcanoes. Instead, the mantle moves with the patience of millions of years, currents of rock rising and sinking in great convection cells. These deep motions are the hidden drivers of Earth's long rhythms. Mantle convection is like a planetary engine. Heat from the core rises upward, pushing material toward the surface, while cooler, denser rock sinks back down. This slow circulation shifts the plates of the crust above, opening rifts, closing oceans, and assembling continents. Over the span of hundreds of millions of years, these movements create a pattern, a cycle in which continents gather together as supercontinents, then break apart and drift into new arrangements. During the Proterozoic, this cycle was in full motion. Around 2 billion years ago, the supercontinent Columbia, also called Nuna, drew together from scattered cratons. Later, it gave way to Rodinia, which held sway for hundreds of millions of years before fracturing apart. Each assembly and breakup was not random, but part of the deep rhythm of mantle convection, the slow heartbeat of Earth's interior. This billion-year pulse shaped the calm of the boring billion. When supercontinents gather, mountain ranges rise, and rivers carry sediments into the seas, affecting nutrient supplies. When they break apart, new coastlines form, altering circulation in the oceans, and shifting the balance of greenhouse gases in the air. The mantle's hidden currents controlled these surface conditions, often without spectacle, but with lasting influence. The stillness we see in the fossil record was, in part, the product of deep stability within Earth's interior. Geologists can read these cycles in the rocks. The ages of mountain belts, preserved in metamorphic minerals, reveal when continents collided. The chemistry of volcanic rocks shows when mantle plumes broke through to the surface. Even the tiny magnetic alignments in ancient minerals trace how continents drifted with the slow turning of the planet's interior gears. Together, these pieces tell us that Earth's heartbeat is real and that it has kept steady time for billions of years. The consequences for life were profound. Mantle convection determined when nutrients were scarce and when they were plentiful. It influenced oxygen levels in the atmosphere by controlling how much organic carbon was buried in sediments. It even played a role in climate, balancing volcanic release of carbon dioxide with the weathering of mountains. For microbes living in shallow seas, these processes were invisible, yet they dictated the boundaries of survival. It is strange to think that life's story is tied not only to sunlight and water, but also to the movements of rock deep below. The mantle, silent and unseen, created the conditions that allowed eukaryotes to evolve, sexual reproduction to spread, and genetic toolkits to refine themselves. Without this deep earth connection, the long stability of the Proterozoic would not have been possible. The heartbeat of the mantle is measured not in centuries or even in millions of years, but in spans of nearly a billion. Each pulse, each cycle of supercontinent assembly and breakup reshapes the stage for life. The boring billion was one such interval, a calm built on the deep steadiness of Earth's interior. And just as the mantle had maintained stability for so long, it was also preparing the surface for change. When Rodinia finally fractured, and when nutrients and oxygen surged once more, the mantle's influence was revealed in the great transitions that followed. From the quiet strength of Earth's interior, we turn again to the surface, where the first glimpses of diversity begin to appear. Hidden in microfossils and chemical traces, signs of early lineages remind us that even during the calmest heartbeat, life was always reaching forward. Beneath the calm seas of the late Proterozoic, life was not as monotonous as it first appears from a distance. For hundreds of millions of years, the fossil record seems to show little more than microbial mats and layered stromatolites. Yet when scientists peer closer, using the tools of molecular biology and the fine details of microfossils, a subtler picture emerges. There were glimpses of early diversity, small signals that the microbial world was richer than the rocks suggest. Among the most telling clues comes from molecular evidence. Modern DNA carries memories of ancient lineages, and by tracing these genetic signatures, scientists can reconstruct when certain groups first diverged. The data suggests that protists, the broad category of single-celled eukaryotes, had already spread into multiple lineages more than a billion years ago. Some were likely algae, capable of photosynthesis. Others may have been predators, feeding on bacteria. Still others drifted as plankton, filling niches that would one day be occupied by more visible creatures. The appearance of algae was especially important. Fossil evidence, including tiny filaments of red algae dating to around 1 billion years ago, shows that photosynthetic eukaryotes were already shaping ecosystems. These organisms added complexity to food webs, providing energy sources for other microbes and beginning to establish the foundations of modern marine ecosystems. Though they were invisible to the naked eye, their presence marked a step toward the diversity we know today. Other clues come from microfossils. the preserved remains of tiny organisms sealed in shales and sediments. Under microscopes, these fossils reveal spherical cells with walls of intricate texture, some smooth, some spiny, some clustered in colonies. Each shape hints at experiments in form and function, adaptations to light, nutrients, or predation. Some may have been cysts, durable resting stages that allowed survival through harsh conditions. Others may represent lineages that no longer exist, small branches of life's tree that vanished before leaving descendants. Together, these molecular and fossil hints reveal a quiet microbial Garden of Eden. The seas were not empty pools, but dynamic environments where microbes interacted in subtle ways. Algae captured sunlight and released oxygen. Protists grazed upon bacteria, keeping populations in check. Some microbes built mats and stromatolites, while others swam freely through the water column. It was a web of interactions, simple by today's standards, yet already showing the outlines of complexity. This hidden diversity also prepared the groundwork for animals. The presence of predatory protists created pressures that encouraged defenses and new strategies. The photosynthetic algae added productivity, enriching ecosystems with energy. The recycling of nutrients by diverse microbes helped stabilize environments, ensuring that oxygen and carbon continued to flow through the biosphere. Though no animals had yet emerged in visible form, the stage was being rehearsed by these smaller players. It is striking to think that the oceans of 1 billion years ago, to the human eye, would have seemed barren. No fish, no corals, no shells, only greenish waters lapping against bare continents. Yet within each drop of seawater, there was a universe of interactions. Each protist carried organelles, passed down from symbiotic unions of ancient microbes. Each algae cell was a factory of sunlight and carbon. Each microfossil preserved in shale was a message across time, reminding us that diversity does not always reveal itself in spectacle. The Garden of Eden metaphor is apt, for this was a world of innocence, without predators large enough to dominate, without animals to graze down the microbial mats, without storms of extinction to reset the stage. It was a time when microbial lineages explored possibilities slowly, each adaptation carried forward across millions of years. These glimpses of diversity show us that even in ages of apparent monotony, evolution never stopped experimenting. From this hidden microbial richness, the story flows into how scientists today are rethinking the label of the boring billion. With each new discovery, it becomes clearer that this was not a wasted span of history, but a crucial interval in which quiet diversity prepared for the revolutions to come. When geologists first began to piece together the vast timeline of Earth's history, they noticed something peculiar about the billion years between 1.8 and 800 million years ago. Compared to the eras before and after, this stretch seemed strangely uneventful. The rocks showed few dramatic shifts in climate, no evidence of mass extinctions, and little in the way of large or complex fossils. To describe this apparent monotony, some researchers gave it a nickname. They called it the boring billion. The name was never meant to be poetic. It was simply shorthand for a period where not much seemed to happen, at least in terms of visible evidence. But as science has progressed, the more we learn about this billion-year interval, the more misleading that label has become. Far from boring, this was an age of hidden revolutions. It was the time when Earth's interior, its atmosphere, and its living systems quietly aligned themselves for the greatest transformations life has ever known. The evidence has been growing steadily. Microfossils reveal that protists, the earliest single-celled eukaryotes, were already diversifying. Red algae appear in the fossil record more than 1 billion years ago, proof that photosynthetic eukaryotes were active long before animals. Molecular clocks, measured in the DNA of modern organisms, point to the silent rise of animal ancestors deep within this interval. These were not events that lit up the fossil record with sudden change, but they were profound steps in evolution, laying the foundation for all later complexity. The rocks themselves hold other surprises. Far from being chemically stagnant, they show the fingerprints of critical shifts. Isotopes of carbon, sulfur, and nitrogen reveal that Earth's cycles were in motion, balancing gases in the atmosphere and nutrients in the seas. The nitrogen cycle stabilized, giving life access to one of its most essential building blocks. Phosphorus, though limited, sculpted the pace of evolution, throttling growth until tectonic changes released more into the oceans. The magnetic field strengthened, shielding the planet from the solar wind. Each of these changes was quiet, but together they ensured that Earth remained habitable and prepared for greater leaps. Even the apparent stability of climate, which at first seemed unremarkable, is now recognized as extraordinary. For nearly 1 billion years, Earth avoided the wild swings that could have reset evolution again and again. The steady carbon cycle acted as a thermostat, preventing both runaway warming and permanent freeze. This stability was not the absence of activity, but the presence of balance, a fine-tuned harmony that kept conditions suitable for life to slowly build its complexity. The more scientists uncover, the clearer it becomes that the name boring billion obscures the truth. This was not a stagnant pause, but a crucial preparation. It was during this interval that sexual reproduction spread, genetic toolkits for multicellularity emerged, and the first whispers of animals appeared. The fact that these changes are not obvious in the fossil record makes them no less transformative. Reframing this period from boring to crucial changes how we think about evolution itself. We are used to celebrating dramatic events, the Cambrian explosion, the rise of dinosaurs, the great extinctions that cleared the way for new forms. But the boring billion reminds us that life's most important steps may unfold in quiet patience. Complexity takes time, and sometimes what looks like monotony is really preparation for revolutions that will come later. This new perspective also carries lessons for how we search for life beyond Earth. A planet that looks stable and uneventful might not be barren. It might be nurturing its own version of a boring billion, slowly preparing the conditions for complexity to bloom. To dismiss such worlds as dull would be to overlook their hidden potential. From this reframing, the story moves to the legacy of the lost billion years. In the oxygen that fills our air, in the genes that shape our bodies, and in the continents that drift across the globe, we still carry the imprint of that long, patient age. When we look back at the billion years between 1.8 and 800 million years ago, it is easy to see it as a quiet plateau, a stretch of stillness with little to mark its passage. Yet the legacy of this lost billion years is all around us. The atmosphere we breathe, the genetic codes that shape our bodies, and the continents beneath our feet all bear the imprint of that long interval. Though the rocks seem to whisper little, the world we live in today would not exist without the quiet transformations of that age. One of the clearest legacies is written in the air itself. After the great oxidation event, oxygen levels rose sharply, but then they stabilized at a relatively low plateau for nearly 1 billion years. This oxygen plateau was not a failure or a pause, but a foundation. By holding oxygen steady, the planet prevented the atmosphere from swinging wildly into instability. Microbes continued to release oxygen through photosynthesis, but it was balanced by the burial of organic carbon and by reactions with the oceans and rocks. This long balance allowed oxygen-sensitive life forms to adapt and refine their metabolisms, laying the groundwork for higher oxygen levels to come later. Without this plateau, the eventual oxygen-rich atmosphere that animals required might never have been possible. The air that fills our lungs today carries the signature of that ancient balance. The legacy also lies within us, in the genetic innovations that quietly took shape during this time. Sexual reproduction, which began during the Boring Billion, created a new way of mixing genetic material. Over millions of years, this shuffling produced diversity and resilience, ensuring that lineages could adapt to shifting conditions. Multicellularity, though only tentative in red algae and other early organisms, showed that cells could cooperate, share resources, and build something larger than themselves. The genes for cell communication, adhesion, and specialization were refined in this quiet era. Complexity did not explode yet, but the instructions for it were being written. When animals finally emerged, they did so with toolkits that had been patiently assembled across the long stillness. Continental cycles, too, left their mark. The assembly of Columbia and later Rodinia showed how the movements of Earth's crust followed deep rhythms, with supercontinents forming and breaking apart across spans of hundreds of millions of years. These cycles influenced climate, nutrients, and ocean circulation. Rivers running off vast mountain ranges carried minerals into the seas. The weathering of rocks helped regulate carbon dioxide, balancing the greenhouse effect under a fainter sunlight. By the end of the Proterozoic, Earth's continents had settled into patterns that resemble the cycles we still see today, establishing the modern style of plate tectonics. The restless motion of continents, the drift of landmasses that continues to reshape our maps, is a continuation of the deep processes that matured during that lost billion years. The most powerful part of this legacy is how much of it remains invisible to the naked eye. A casual observer of Proterozoic Earth would not have seen animals roaming or forests rising, yet the invisible changes were more profound than the visible ones. The air was learning to hold oxygen, genes were learning to combine, share, and innovate. Continents were learning their rhythm of gathering and scattering. These were not fireworks, but the laying of foundations, the quiet architecture upon which all later revolutions would be built. When we trace the threads of our own existence, they all pass through this lost billion years. The mitochondria that power our cells, the chromosomes that shuffle in reproduction, the oxygen that flows through our blood, and the continents that shape the world's climates are all gifts from that quiet age. Its silence was not emptiness, but preparation, the patient shaping of a world that would one day burst into the Cambrian explosion. From this recognition of legacy, the story moves gently toward reflection. The lost billion years remind us that stillness can be as creative as chaos, that silence can carry as much weight as sound. And as we prepare to step into the final chapter, we see that the Boring Billion was not boring at all, but one of the most crucial intervals in the entire history of Earth. As we step back from the long journey through the Proterozoic, it becomes clear that the so-called Boring Billion was anything but dull. It was Earth's longest breath, a billion years of silence before the chorus of animals, plants, and forests erupted into view. For nearly a billion years, the planet seemed to wait, its rhythm steady, its seas calm, its skies unchanging. Yet within that stillness, the foundations of everything familiar were being laid. It is easy to be drawn to the dramatic chapters of history, the great extinctions, the fiery eruptions, and the sudden blooms of life. But there is something even more humbling about this quiet interval. It reminds us that change does not always come in bursts of chaos. Sometimes it arrives in patience, in stability stretched across spans too vast for human imagination. Even stillness can be profound, for it is in stillness that preparation occurs. The oxygen plateau, holding steady for ages, set the stage for the atmosphere we breathe today. The genetic experiments of single cells, unfolding quietly in the shadows of microbial mats, created the toolkits for complexity. The slow cycles of continents assembling and breaking apart taught Earth how to regulate its climate and circulate nutrients. Every breath of air, every beat of our hearts, every step upon solid ground carries with it the legacy of that lost billion years. Imagine the world as it was then, oceans rich with microbial life, invisible dramas unfolding in the smallest of scales, continents drifting slowly, shaping currents that carried nutrients into shallow seas, volcanic skies balancing greenhouse gases while the sun shone faintly above. There were no forests or coral reefs, no dinosaurs or mammals, yet the seeds of all these futures lay hidden in the genes of fragile eukaryotes and in the patient chemistry of the seas. In many ways, this was Earth's rehearsal, a time of practice before the performance. The chorus of animals that would fill the Cambrian seas was already being composed in silence, each genetic note written carefully across millions of years. When the moment came, and oxygen rose higher and nutrients flooded the seas, the world was ready. The Cambrian explosion was not a sudden miracle, but the release of potential stored across the long stillness of the boring billion. What we learn from this chapter is that the world is not shaped only by drama, it is also shaped by patience. The billion-year calm was not wasted time, but a reminder that progress can come quietly, that preparation can be as important as action. Without it, the Earth we know would not exist. Without it, we would not exist. And so, this so-called boring interval becomes something else entirely. It was not boring, it was crucial. It was a billion years of stability that allowed life to gather strength. It was Earth's deep meditation, a silence that changed the world. If you have found comfort in this journey through deep time, it would mean so much if you gave this video a gentle like and perhaps subscribed, so more curious minds can discover this peaceful corner where science and story come together. And if you feel like sharing, tell me in the comments where you are listening from and what time it is there. I love seeing how these quiet explorations travel across the world, connecting us through the vastness of space and time. As you drift onward, remember this: even in silence, the world was moving. Even in stillness, life was preparing. The earth itself once rested for a billion years, and in that rest, it created the possibility of us. Now take a breath, soft and steady, and let your thoughts settle like ancient sediments at the bottom of a calm sea. The story of Earth's lost billion years has closed, but the wonder it carries flows quietly into the present, into you, into all of us.